Hello, fellow Rustessians, and welcome to a new episode of Hello Rust. I'm Matthias, and today we talk about something that I do very regularly at work, which is, working with Go. I kind of like Go and I kind of hate Go for different reasons, and maybe some of the reasons will become apparent during this session. What I'm going to show you is some code from a book called Go in Practice from Matt Butcher and Matt Farina. We will see a small sample code and we will compare it with some Rust equivalent and see why Rust is better in terms of safety when it comes to concurrent execution, and just getting a feeling of how the different languages work in practice and how they behave. Yeah, so stay tuned. Our task is pretty simple. Say we have a big corpus of text, maybe the complete works of Shakespeare, which I just happen to have around here, and you want to analyze which words occur more than once in any work of Shakespeare. Alright, here's the text that we are trying to parse. We want to parse each word one by one. So we split it every whitespace character and analyze the words. Here's the Go code that tries to achieve that. First off, every Go code needs to be in some package. By convention, this is the main package for your main entry point. Then we have a couple imports. Don't worry about those in the beginning. We have a main function. And here's the interesting part. We make use of a wait group, which is a way to synchronize work between workers. And we get our new word status structure, which is defined as a map from string to int. So string is the word, int is the count. We iterate over each input argument. And the arguments are the file names with the text in it. And we take everything from the first from the second to the nth argument, because we skip the first argument. That is usually by convention, at least on Unix machines, it is the program name, and we don't want to parse the program name. So we skip that. For each file, we add one to the wait group. And once this execution is done, we set this wait group to done again, which will simply decrease this counter. And the wait group is done when the counter is back to 0. Pretty simple mechanism, but pretty effective, pretty pragmatic, just like Go. In our loop, we have a function here, which takes a file name, and then it calls tally words on this file. Tries to analyze the words and do some error handling here. If we have an error, we simply print it. So we don't exit, we try to parse the remaining files in any case. Yeah, that's pretty much it. We have this loop down here, which iterates over all words that we found. And if the count is bigger than 1, then it will print the word and the count. Actually, the count and the word. Yeah. And what does this tally words thing do? It opens the file, checks for errors. It has this defer clause in here, which means before we exit this function, close it. Pretty pragmatic as well. Pretty standard Go thing to defer the close. Then we use a buffer for scanning the file and splitting it word by word. We improve I/O performance with buff I/O scanner. Then we can call scan on our scanner, and that just returns one word each as an iterator until it's done. And we just take this word, we get the text from it, we transform it to lowercase, that is our word, and then we add this word to our dictionary. And if there's any error during the scan, then we return that. Otherwise, it will return nil, which means no error occurred. Now the interesting part is our add function here. And add, actually it's a method. It's a method on words. It takes a word and it takes an n and it adds n to this dictionary. So it checks if the word is already in our dictionary. If not, then add it to our dictionary. Otherwise, get the current count and add n to it, which is the new count. Yeah, pretty straightforward, you might say. Let's just run it and see what happens. And the way you run it is you say go run race.go, and then I just have some text files here which I use as an input, and in the end, after this function, I will also sort the output by the number of counts for each word. That's at least the plan. So let's run it. Ooh, surprise. We got a nice error. It seems like we spawn a lot of Go routines here. Go routine 7, 6, 5, and so on. They all do scanning, it seems. But one of them, which is Go routine 8, it crashed. And yeah, some back and forth. Exit status is 2, and the error message is concurrent map read and map write. Well, you might say, of course, obviously, we do that concurrently because we have a lot of files and we have this wait group, remember? So what can go wrong? Well, it turns out what we do here is we take this dictionary and we mutate it with different threads at the same time. So we have multiple mutable references to the same point in memory. And well, that can cause a race condition, as has happened here. So of course you want to avoid it. And the way you can avoid that easily in Go is by having a mutex lock. So before we write something to our dictionary, we lock it, and after that we unlock it for some other concurrent access. Let's do that. So now our word structure takes another thing, which is a mutex. And if we try to run that, it still won't work because we run into the issue where we have an early return here. So the common practice is to defer the unlock right after the lock. If we try to run that, we're good now. You can see that the only thing that we did was adding a lock here. Okay, that's easy, but the problem is that the compiler doesn't help you with that. Okay, you run it and then you get an error message at runtime, which is also pretty explicit, and you know that you have multiple mutable access, but you don't get this information at compile time, which is where you usually want to have this kind of thing happening, not in production somewhere. And I have to say, this is one thing that I don't really like about Go. And I guess the core problem is that Go doesn't have a concept of ownership. Ownership in Rust prevents those kind of issues, and you will later see why. But the basic concept is that you can only have one mutable access to one point in memory, and there always needs to be a clear owner. So you might say, okay, why does this help me in terms of concurrent access? Because I definitely want concurrent writes. Yes, you want them, but you want to have sequential access to the dictionary. All right, I created this new main file, and we can just start playing around in Rust, shall we?
Yeah!
I guess we need a main function. And there we iterate over the environment variables. And we already skipped the first one because we know that's the application name. And for each application name, let's just first print what we have here. We have none, and then if we add some arguments, 1, 2, 3, well, we get 1, 2, 3. Now for each argument, we want to parse that. And this is where our tally words function comes into play. We say tally words, and it takes our words dictionary, which we haven't really created yet. Let's say let words equals hashmap new, and it takes the argument name. Let's make that the first argument to be coherent with the Go version. To simplify things, let's make that an own string because it's a stir by default. And this we just want to borrow mutably. Okay. And after that we say for word in words. Actually, this is a count iter. If the count is bigger than 1, print line count word. Now let's write our tally words function, which is a string. The other one is our words hash map. Returns a result. Now let's return no result at first. Let's just return nothing for now. Okay, there's a nice function to read file name. There's a nice function to read the file contents into a string. Let contents equals fs read to string file name. That can go wrong, so we expect an error here. Let's import fs. I wonder why there's no syntax highlighting. Anyway, for word in contents.split whitespace, let's rename that to s. Let key equals s to lowercase. Then we use the entry API, which we've seen in the very first episode. Very, very handy thing for hash map access. Let's say words.entry key or insert 0 plus equals 1. That means take the entry. If it's not there, set it to 0, which is our default, and then add 1 to it. Pretty succinct. Succinct? Okay, so probably I will get a bunch of errors when I try to compile this, but yeah, I'm adventurous. Cargo build. Yup. First off, yeah, that's why the syntax highlighting didn't work anymore, because I forgot an angular bracket. I need every time standard collections hash map, and it's not words, it's W. No, should be words. Okay. Yeah, and now We have some ownership problems. We definitely want this to be mutable, so and mute words. Oops. That should go next to the type. And now the only thing left we need to do is making this mutable. And we're done. Almost, because this is the sequential version. I'm not sure if it will run, but let's see. Cargo run, giving me the text. We don't want to time this. Yeah, it seems to work, and it also seems to produce the same output as we had before. So that's at least a win. But now we want to make that concurrent. Okay, probably we will go into proper concurrency in one of the next episodes. But if you want to do something simple and you want to quickly make something concurrent, then usually I suggest to use rayon for that. Rayon is a crate which does all the concurrency in the background, and it's perfect for simple use cases like this. The only thing you need to do is cargo add rayon. You need to use it. So extern crate. No, why not just use the handy suggestions? Yeah, rayon. There we go. And rayon takes everything that can be iterated and makes it parallel. What you have to do is making something into a functional or iterator pattern, but it's not that hard if you know what you're doing, as everything. Okay, so the way to rewrite this in a more functional way is saying env args skip 1 iter for each arg, and then our function. Now I'm pretty sure this will not compile, and I will tell you why. It says no method named iter found for type iter skip blah blah blah. I guess we can get rid of iter here. Yeah, now I remember why I wanted to have iter here. Because a normal iteration can be transformed into a rayon parallel iteration by saying pair iter instead of iter. So if we had an iter here, we could make it a pair iter without changing anything else, and it would just parallelize stuff. First, I want to have an iter here, and for that I have to collect that into something like a vector of string. No. Like this. Yeah. And this is something that we can iterate over. So it's this way around. And here comes the magic. The only thing I do is making pair iter out of iter. And this will make something parallel, but now here comes the problem. Oops. That was not the problem I'm trying to show you, but yeah, it needs this trait to be in the scope, but usually what you do is you use the rayon prelude. Yeah, this is the error I wanted to show you. It says cannot borrow data mutably in a captured outer variable in an fn closure. Well, that's quite a mouthful, I agree. Here's what happened. We have a function here, tally words, And that wants to take words mutably and borrow it. So this is the first part. Cannot borrow data mutably in a captured outer value. What does captured outer value mean? Well, words is captured. It's an outer value. It's defined in line number 9. And now we want to capture that in our fn, in our function, in our closure. And we cannot do this. The reason is that we have concurrent access then. And that's a race condition. So Rust prevents us from shooting ourselves into the foot here. In my opinion, it's not really the best at describing this issue right now, but at least this code won't compile, so it cannot fail in production. And the solution to that is the exact same solution that we use on Go. We use some kind of mutex. Maybe there are some other solutions, but this is one straightforward thing that we can just port straight over from Go without thinking too much about it, and it will solve our error here. Let's use a standard sync mutex and wrap our hash map around this, map a mutex around this hash map. Now, without changing anything, it will tell us, well, okay, now we have mismatched types. We're using a hash map, but we want a mutex here. And that's because in our tally words function, we expect a hash map, but this should be a mutex now. And here again, we have a mutex. We need to lock that first. We get a mutex guard out of it. We have to unwrap that. And down in line number 30, we don't have an entry thing for the mutex anymore. Instead, we also need to lock here and unwrap again. Don't worry, we will take care of error handling later. Now we get rid of this mute statement here. And down here. And at least our code compiles again. We haven't dealt with error handling yet, but the most important part now is that this code is absolutely thread safe. Without us doing much of the work, it's mostly Rust doing the work. Let me move over this thing here real quick. For me, that is one of the beautiful things of Rust. It will guide me into the right direction. I don't really have to think much about it. I just have to follow the compiler advice, and then I reach a point where the code is much better, much more idiomatic, much simpler, much easier to maintain. We don't really pass a mutable borrow anymore to our tally words function because we don't really mutate the hash map. We need a borrow to the mutex that owns the hash map, and that's a big difference. This way we can also get rid of the mute here. What I don't like about it is that we use some unwraps. We will get rid of that now. But first, let's see if it produces the same result as before. It does. Okay, let's do some proper error handling. The first unwrap that I see is in line 18, and personally, I don't think it's a very big deal. We might get away with just using an expect and writing some proper error message here, something like cannot lock mutex for words or something. Maybe something better that you can come up with. Of course, we could have a result as a return type and have our own error type. If I get rid of this expect, just use the carrier operator, What will I get? Not found in the scope, of course, but if I define an error, let's say tally error, and that's gonna be log, and we derive debug. Won't work because of our return type. We need an OK down here, and then the compiler will tell us, wait, yeah, we cannot convert from a poison error to a tally error. Okay, we could implement that now. We'll just copy that in and adjust it real quick. Okay. Oops, we need to use that. Poison error, import it into our namespace. Okay, back on track. What I did was having a default impl for poison error for our tally error, and we just converted to a tally error log. Why not? And then we can use this beautiful carrier operator here. Here we could now return a result. Let's make that a result of the unit type and our tally error. Carrier operator here. Same thing. We need an OK type for the case where everything went well. And then we can propagate our error in our main function with the carrier operator. And we need the same thing. We need a conversion from standard IO error into our tally error. Some copy pasting. Let's add an IO error here. Let's try again. Whoopsie. No constraints. Right. Our for each method, it returns a unit type. A cheap way of doing this would be to use expect here and have an error message. This would, of course, get rid of the error message, but it's not really idiomatic. It doesn't really feel good. I just realized that I wasn't really introducing for each properly, so let's do that. For each is a function which takes a self, so actually it's a method, and then it takes an f, which is an fn mute, so a function, a closure, if you like, and it doesn't return anything. It has no result. It returns a unit type, if you like, but it doesn't return a result or anything. So we have to deal with the error inside of this for each, or use a different function and then collect our results. For example, we could map on our argument and then collect into a vector of results and then do whatever we want with those results. But that's a bit out of the scope for today. Anyway, there's a very nice blog post about this kind of thing. Let me look it up real quick. Yeah, it's from Karol Kuczmarski, and it's called Iteration Patterns for Resultant Option. And in here, There's a lot of different iterative patterns on what you want to do when you have a result, and how to collect all errors, how to collect only the first error, and so on. I guess what this showed was the different ways how Rust and Go handle concurrency. And maybe you can now understand why I prefer the Rust model over the Go model for this kind of things. You can, as always, find the code on the Hello Rust Show GitHub repository. I would be very glad if you could send in some pull requests if you found bugs. Other than that, thank you very much for watching once again. If you like the show, of course, you can support it through Patreon. I have a Patreon account and I do all of this in my free time. So if you enjoyed the content and you want to keep it free, then please think about donating on Patreon. Also, think about subscribing on YouTube and getting informed about new shows. I guess that's it for today. Hope you had some fun and see you next time.